Problem number 6 in Advanced Classical Mechanics Practice Final Exam. So let a one-dimensional Hamiltonian system have h q comma p equals p squared over m plus lambda q to the 6 minus u q squared, where lambda and mu are greater than 0. And I should have said that's mu. Sorry about that. So part A, write Hamilton's equations. Part B, locate all fixed points in phase space. Part C, classify their linear stability. Part D, explain why Hamiltonian flow preserves phase space area. And part E, relate this to Liouville's theorem. Okay, so this is Hamiltonian flow in symplectic structure problem. So we could say that the Hamiltonian is hqp equals p squared over 2m plus lambda q to the 6 minus mu q squared, where lambda and mu are greater than 0. So Hamilton's equations are q dot equals the partial derivative of h with respect to p equals p over m, and p dot equals negative partial h with respect to q equals negative 6 lambda q to the 5th plus 2 mu q. Okay, so here the fixed points satisfy here. Q dot equals 0 and p dot equals 0. So p equals 0 and negative 6 lambda q to the 5th plus 2 mu q equals 0. And then 2q times the quantity mu minus 3 lambda q to the 4th, that equals 0. So solving here, we're going to get q equals 0, or q to the 4th equals mu over 3 lambda. So the fixed points are q comma p equals 0, 0, and q comma p equals this plus or minus quantity here, mu over 3 lambda raised to the 1/4 comma 0. And if we define v of q equals lambda q to the 6th minus mu q squared, then v prime of q equals 6 lambda q to the 5th minus 2 mu g. And v double prime of q equals 30 lambda q to the 4th minus 2 mu. So if we go ahead here and we linearize Hamilton's equations around a fixed point, that gives us this column. Delta dot q, delta dot p, my apologies for the deltas, and that equals this matrix here, first row 0, 1 over m, second row negative v double prime of q naught and 0, and then this column delta q, delta p. Sorry about that again for the way that that's drawn. I do not draw or construct omegas or deltas well. Okay. Now from here, what we could say is, building on this, the eigenvalues satisfy sigma squared equals negative v double prime q naught divided by m, and at q naught equals 0, v double prime of 0 equals negative 2 mu. So sigma squared equals 2 mu over m, and that's greater than 0. So the eigenvalues are real. Sigma equals plus or minus the square root of 2 mu over m. So we could say that 0, 0 is an unstable saddle point, and at q naught, that equals plus or minus this term mu over 3 lambda to the 1/4, and q naught to the 4th equals mu over 3 lambda. So building on that, v double prime with q naught equals 30 lambda times mu over 3 lambda minus 2 mu, so that's going to equal 10 mu minus 2 mu equals 8 mu. So from there, sigma squared equals negative 8 mu over m. That's less than 0. So that would mean that the eigenvalues are imaginary, because sigma is going to equal plus or minus I times the square root of 8 mu over m. And that would now yield plus or minus mu over 3 lambda to the 1/4 comma 0, and these are linearly stable centers. So from there we could say the potential V of Q equals lambda Q to the 6 minus mu Q squared has a local maximum at Q equals 0 and two symmetric minima at Q equals plus or minus the quantity mu over 3 lambda raised to the 1/4. Now, adding on to this, I should have put this on the first page. The phase portrait, I wanted to mention this, that the phase portrait has a saddle at the origin, two stable centers, and separatrix curves passing through the origin. That's another word I've heard pronounced different ways by professors. For energies below the saddle energy, E equals 0, trajectories oscillate in one of the two wells. And for energies above E equals 0, trajectories pass between both wells. So since V of Q approaches positive infinity as the absolute value of Q approaches infinity, we could say that all finite energy trajectories are bounded. Finally, Hamiltonian flow preserves phase space area. The phase space velocity field is V. That should be an of. That's not an epsilon. My apologies there. That should be V parenthesis Q comma P close parenthesis. Not an epsilon. Sorry about that. Equals this partial derivative of H with respect to P comma negative partial derivative of H with respect to Q. Okay, so building on that with the divergence, what we could say here is its divergence is that del operator or nabla. So its divergence is del dot V equals this partial with respect to Q, and then this partial derivative of H with respect to P, plus this partial derivative here respect to P, partial negative partial derivative of H with respect to Q. And what happens in this situation is that since these mixed partial derivatives commute, del dot V is going to equal that following second partial derivative of H with respect to Q and P minus the second partial derivative of H with respect to P, Q. And that's going to come out to equal to 0. So del dot V equals 0. So the Hamiltonian flow is incompressible in phase space. So this is the, sorry if I wrote the twice. So I should have said this is, sorry about that, the one-dimensional version of Liouville's theorem. And that's another name I've heard pronounced differently by professors. I'm definitely not a foreign language expert, so I cannot confirm how to properly pronounce a lot of these names. My apologies. Again, Hamiltonian evolution preserves phase space volume. And for this system, phase space volume means phase space area in the PQ plane. Okay, so the math and the physics here are okay, but the pronunciation of some of these names, I apologize in other videos too for that. Again, I'm not good at that. Thank you very much, and that's problem number 6, and have a great day.